Okay, so today we're going to talk about the next set of periodic trends. So the first one that we're going to look at is ionization energy. So remember from the activity we did today, ionization energy is the energy required to remove an electron from the outer orbital. So in our examples here that we're going to compare, we have oxygen, fluorine, and chlorine. So oxygen and fluorine go across a period, so we're going to look at those first. Oxygen, you know, has 8 protons and 8 total electrons, and then fluorine has 9 protons and 9 electrons. So if we think back to what we learned from last class when we talked about nuclear charge, okay, the proton to electron ratio here is 8 to 8, so that pole is coming from the 8 protons. Over here we have 9 protons pulling in. Okay, so there's a stronger pull from our fluorine than there is from our oxygen. Okay, so if we're trying to pluck an electron from the outer shell, okay, it's going to take some energy. So the more pull towards the nucleus, the more energy it's going to require to actually pull that electron off. So because this one has more pull, it would have a greater ionization energy than oxygen would. Now, neither of these actually want to lose an electron because they are anions and they want to gain electrons, which we learned a couple of class periods ago. So both of these energies actually are really high energies compared to, say, the cations on the other side of the periodic table. But because fluorine has more protons than oxygen, it will have a greater pull, therefore a greater ionization energy to pluck that electron off. As we go down the group, okay, we have fluorine here has 2 energy levels of their electrons, and chlorine has 3. So then we have to start thinking about that nuclear shielding. Remember, the shielding is the electrons in the middle of kind of that buffer, and the bigger the buffer, the easier it is to pull an electron off. So fluorine here, since it has only 1 orbital of buffer in the middle, okay, takes quite a bit of energy to pull an electron off that outer shell. This one has 2 energy levels as its buffer from the protons pulling in. So it'll be a little bit easier, require less energy to pull an electron off its outer shell. Okay, so the ionization, if you look at it this way, fluorine has a higher ionization energy than chlorine does. It's easier to pull that electron due to nuclear shielding. Okay, so then if we look at the trends for the periodic table over here, okay, we can say as we go down this way, okay, we are decreasing our ionization energy, okay? Requires less energy to pluck an electron. And then as we go this way, due to nuclear shielding, right, not shielding, nuclear charge, that would increase the amount of energy that it takes to pull that electron.
All right, now we're going to talk about electronegativity. And electronegativity is the ability for an element to attract an electron from another atom. So the stronger that nuclear charge, or the stronger that pull in from the nucleus, the more that they're going to be able to pull an electron from somewhere else. So, for example, if we go across the row and we look at oxygen and then fluorine, both have those 2 shells of electrons. But because fluorine has 9 protons, where oxygen only has 8, the fluorine can pull the electrons from another element in a lot easier than oxygen can. So, because it has a higher nuclear charge, it can grab an electron from something from over on this side of the periodic table, say sodium, than oxygen could. As you go down a row, though, even though we're increasing the amount of protons in the nucleus, we're also increasing that amount of shielding. So we're adding another energy level. So the 3 energy levels on chlorine shield more than the 2 energy levels do on fluorine. So even though chlorine has a greater nuclear charge or nuclear pull. Because of the shielding, fluorine will actually have a higher electronegativity. It's going to be able to attract an electron much easier. So this is kind of the opposite of that ionization energy that Ms. Ruby was talking about, where ionization energy is how much energy you have to put in to remove an electron. So how much energy I have to put into chlorine to get it to give this up is relative to how much energy the chlorine uses to actually pull an electron, or how attractive it is. So as we look at our periodic table, as we go across a row, we increase, and as we go up a column, we increase. Making fluorine right here our most electronegative element on any periodic table. Keep in mind that our noble gases, they don't attract electrons to themselves because they're already satisfied, so they don't need another electron to fulfill their octet. So our noble gases don't have an electronegativity, so they'll be left off your electronegativity chart when we get there. So now we're going to talk about our last trend, which is reactivity, which should bring you back to your periodic table lab from last week. So reactivity is how readily an atom reacts or bonds with another atom. So how quickly we can get chlorine, or how easily we get chlorine to bond with something else. So as you can imagine, our noble gases have no reactivity, so we're going to leave them off our periodic table for now and ignore them. But first we're going to talk about gaining electrons, because we know that there are two ways that atoms become ions, and they become ions to fulfill their octet and then make bonds, which we'll talk about next few minutes. But atoms can either gain electrons, so they can pick up electrons from somewhere else, or they can give up their electrons. So these elements, which are all in this top corner of our periodic table, really are so close to full that they don't want to give up any of their electrons. They want to gain their electrons. Fluorine, remember, has that really high electronegativity, so it's pulling and pulling and pulling on electrons from other atoms. So fluorine has the highest reactivity, or it's the most readily reactive element in our halogen family, because it gives up, or it gains, all of its electrons really easily. So as we get closer, as we get further into this corner, if you consider the periodic table and the trends that we've talked about so far, it should make sense that these guys up here are really electronegative, so they're pulling in electrons really easily. They have really low ionization energies. They have high ionization energies because they don't want to give up their outer electrons. But they're small enough that they can actually pull electrons from somewhere else. So these guys up at the top here are really, really reactive. All right, so we've talked about gaining electrons. Now we're going to look at losing electrons. So some elements would prefer to gain electrons to fulfill their octet. Some elements, like these guys on the left-hand side of our periodic table, would prefer to lose their electrons or have their outer electrons plucked off so that they have a full outer shell. So like this is lithium, sodium, and magnesium, which are right about here in our periodic table, right? So the reactivity on one side, because remember we talked about reactivity is just atoms reacting, or atoms bonding. They're giving up or gaining electrons. On the right-hand side, increases as you get to those elements that more want to gain or have a higher electronegativity. On the opposite side of the periodic table, these guys would all prefer to give up their outer electrons so that they can fulfill their octet. So the closer that they are to already having a full outer shell, the easier it's going to be to pull that electron off. Also, as you go down the rows, because there's more energy levels between the nucleus and that outer electron, we can pull off the electrons on the outside much easier. So sodium's outer electron can get pulled off a lot easier than lithium's can, because sodium has more energy levels, so less pull from the nucleus to hold it together. So as we go down towards this corner, we increase, making francium, which is down here in this corner, our most reactive element on that side. So that's our most reactive element that wants to lose an electron, And fluorine is our most most reactive element that wants to gain an electron. All right, so once again, you've watched video 2 now. So the password for the haiku formative is plucking, P-L-U-C-K-I-N-G. And you have until Monday at 7:30. And I know some of you don't have class Monday with us, but we want to get all that data so that we can go ahead and run class on Monday. So.